Okay, good morning, everybody at our YouTube channel. And thank you so much, Adelmo Ortiz Conde, for taking your time and giving this presentation to us. First, I will make a brief introduction of Adelmo Ortiz Conde. He received the Professional Electronics Engineering degree from Universidad Simón Bolívar in Caracas, Venezuela in 1979, and the ME and PhD degree from the University of Florida in Gainesville, United States in 1982 and 1985, respectively. From 1979 to 1980, he served as an instructor in the electronics department at Universidad Simón Bolívar. In 1985, he joined the technical staff of Bell Laboratories in Reading, United States, when he was engaged in the development of high-voltage integrated circuits. In 1987, he returned to the electronics department at Universidad Simón Bolívar, where he was promoted to the full professor in 1995. He was on a sabbatical leave at University of Central Florida in Orlando from January to August 1994, and again from July to December 1998. He also was on a sabbatical leave at University of Central Florida, Orlando, from January 1994 and again from July to December 98. He was on a sabbatical leave at Centro de Investigações e Estudos Avançados, CINESTAD, in Mexico City, from October 2000 to February 2001. He co-authored one textbook, Analysis and Design of MOSFETs, Modeling, Simulation, and Parameter Extraction, in 2012 by Springer. And he also authored over 190 international technical journal and conference articles, including 20 invited review articles. His present research interests include the modeling and parameter extraction of semiconductor devices. Dr. Ortiz Conde is an electron devices distinguished lecturer and the chair of the IEEE's gas electron devices and power electronics devices Venezuela chapter. He was editor of IEEE Electron Devices Letter in the area of silicon devices and technology from 2009 to 2018. He was the Region 9 editor of the IEEE Electron Devices Society newsletter from 2000 to 2005. He's a member of the editorial advisory board of various technical journals, including Microelectronics and Reliability, Universidade Ciência e Tecnologia, and Revista Engenharia UC. He regularly serves as a reviewer of several international journals and conferences. He was one of the founders of the first IEEE International Caracas Conference on Devices, Circuits and Systems, ICCGCS, in 1995. In order to make it more international, this conference changed its name to International Caribbean Conference on Devices, Circuits and Systems, ICCGCS, in its sixth edition in 2006. Since 2019, this conference has been sponsored by the IEEE Electron Device Society under the name IEEE International Latin American Electron Device Conference, also known as LAEDC. By the way, this year is going to be in July in Puebla, Mexico. So thank you so much, Adelmo, for taking your time and joining your knowledge with us with this Electron Devices Society distinguished lecture. Thank you so much, and the floor is yours. Thank you, Adelmo.
Thank you very much. Thank you very much for the nice presentation. It is a pleasure to visit Brazil virtually, and of course, it is better to visit real, but You cannot always travel all the time, no? Okay, let's go with my presentation. The outline of my presentation is the following. We will start with the origin, then we will go to the evolution, we will talk about Moore's law, we will talk about SOI MOSFET, then multi-gate three-dimensional SOI devices, then we will talk about the FinFET, then we will talk about a device that has very many different names. This device is called force-sheet, nanosheet, nanobeam, nanoribbon, gate all-around, multi-bridge channel FET, and ribbon FET. This device is replacing the FinFET in the present time. Then we will talk about the recent development, the RF application, and finally we will go to summary. Here is a view graph that describes the evolution of electronics. Start with 1906 with the vacuum tube. Then 20 years later in 1926, the idea of the MOSFET. This was presented in a patent by Lilienfeld. Lilienfeld, 2 years later in 1928, presented the idea of a MOSFET. Then in 1935, it was presented the idea of the inversion MOSFET. Then year 1947, the fabrication of the first transistor. This was the point contact transistor. It was fabricated by Bardeen and Brattain, and a few months later, William Shockley presented the idea of the bipolar transistor, bipolar junction transistor in 1948. The three of them, Bardeen, Brattain, and Shockley, received the Nobel Prize of Physics in 1956. Then the hybrid integrated circuit. Then the planar integrated circuit. The integrated circuit was received also the Nobel Prize in year 2000, I think. Then the CMOS circuit in 1963. The fabrication of the MOSFET in 1960. Then Moore's law in 1965. The fabrication of the first microprocessor by Intel in 1971. That was a 4004. Then the NR scaling rule in 1974. And then about 20 years later, the miniaturization deviated from the NR scaling rule, and then new things has to be done. For example, a strained silicon in year 2002, high-K metal gate transistor in 2007, and then the FinFET 3-gate transistor in year 2012, and the gate all-around on nanosheet in year 2021. Here is an interesting view graph that describes the time between invention and commercialization. This view graph is taken from Spectrum. The article is called The Ultimate Transistor Timeline, the Transistor Amazing Evolution from Point Contact to Quantum Tunnel, and that was in December last year. And this view graph presents the following. For example, the point contact transistor was invented at this time and was commercialized in a very short period of time. On the other hand, there are devices, for example, the heterojunction bipolar transistor, which was invented here and was commercialized here. So it took a long time to be commercialized. 1906, the vacuum tube or trio was invented by Lee Forest, and this is the view graph of the vacuum tube. Then year 1926, the idea of the MOSFET. It was presented by Lilienfeld, and it was granted in January 28, 1930. The patent was entitled Methods and Apparatus for Controlling Electrical Current, and this was the idea of the MOSFET. So you have a semiconductor, you have a contact here, you have a contact here, and you have here the gate. It was essentially a MOSFET, what Lilienfeld presented in 1926. 1928, the idea of the depletion MOSFET. It was presented also by Lilienfeld. The patent was entitled Device for Controlling Electrical Current. It was requested in March 28, 1928, and it was granted in March 7, 1933. The device was this one. It was a semiconductor. Semiconductor. It was here. Then it has oxide here. It has a contact here, which is source. Here it had a contact, which is drain. And here is a contact, which is the gate. So it was essentially an on-top depletion single bottom gate SOI MOSFET. Here is a reference to the patent. 1935, the idea of the inversion MOSFET. It was presented by Oscar Hill, and it was essentially an on-doped inversion single-top gate-SOI MOSFET. Here is a reference. Year 1947, the first transistor is fabricated by Bardeen and Brattain. The transistor is described here. It's a semiconductor, a contact here, and a contact here. This is emitter, this is collector, and here is the contact to the base. It was called base because it was the physical base of the device. And Bardeen and Brattain were trying to fabricate a MOSFET. And in fact, Brattain wrote many years later, Bardeen and I were simply trying to make a good field effect device, and as a result, we were put in a position to observe for the first time a phenomenon now called the transistor effect. Here are the references. So it's very interesting that they didn't have any idea of how it was working. In fact, this device, the point contact transistor, has two possible explanations, and nowadays we really don't know which is the correct explanation. Nevertheless, this device was fabricated for a very short period of time, and this device, a few months later, allowed William Shockley in 1948 to present the idea of the bipolar junction transistor. Bardeen, Brattain, and Shockley received the Nobel Prize in 1956. Shockley wrote many years later, "What I say about myself, and I am sure most creative people will say the same thing, is that when we look at how long it took us to get certain ideas, we are impressed with how dumb we were, on how long it took us, and how stupid we were. But we have learned to live with this stupidity and to find from it what relationship we should have seen in the first place." So I like very much this sentence, because this sentence gives you the hope that you will solve a problem when you are trying to solve a problem and the problem is difficult, especially for the graduate student. So, well, remember, if Shockley used to think like that, well, you should keep working and, you know, don't get frustrated. According to Riordan is an expert in the evolution of the transistor, and he writes in IEEE spectrum, and here are the reference. So according to Riordan, the most important invention of the 20th century was conceived not just once, but twice. So in Paris, two German physicists, Herbert Matare and Henry Welker, built a point contact transistor in June 1948. So that's a few months after Bardeen and Brattain. Then 1958, the hybrid integrated circuit. It was presented by Jack Kilby. So this is the hybrid integrated circuit. It was not really a complete integrated circuit as is known today, but it was very close to be an integrated circuit. And Jack Kilby received the Nobel Prize in Physics in year 2000 for this contribution. He was working at Texas Instruments. 1959, the planar integrated circuit. This is a real integrated circuit. It was done by Robert Noyce from Fairchild, and I think he would have probably received a Nobel Prize, but he died on June 3, 1990. 1960, the fabrication of the MOSFET. Here is the reference. Kahng and Atalla. Here is Dawn Kahng and here is Martin Atalla. And this was the first MOSFET fabricated in 1960. The MOSFET was fabricated in 1960, even though it was invented by Lilienfeld in the year 1928, but it took a long period of time to be fabricated because the problem was there was not a good oxide. So because the oxide quality was not good, they could not fabricate a MOSFET. 1963, the invention of the CMOS circuit. So here is, for example, an inverter using CMOS. And as you know, the importance of this circuit is when one device is working, the other device is off, and it is supposed to have zero current. And this allows the evolution of the digital circuit. And it was invented in 1963 by Frank Wanlass and C.T. Sah. Here are the references. It was a journal, and it was also a patent. 1971, the first microprocessor, the 4004. This circuit has 2.3 10 to the 3 transistors. It has an area of 12 millimeter square. The frequency was 108 kilohertz. It used a technology of 10 micron. It used PMOS, 12 volt. The energy was 0.3 watts, and it worked with 4 bits. And here is the reference. It is interesting to mention that the first microprocessor was really a pet project in Intel, and it was designed by the Japanese that Intel was doing for them. And the first microprocessor took a long time to be commercialized, because this circuit used to belong to the Japanese company that fabricate calculators, and the Japanese company allowed Intel to sell the microprocessor, I guess about 1 year later. Moore's law in 1965. This is the original plot by Morse, and the original plot of Morse by Morse has only 5 points. Here we have the number of devices in an integrated circuit in a logarithmic scale. Here we have the year, and Morse has only 5 points. And with these 5 points, he was able to predict that this behavior was going to be maintained for several years. The original article was presented in Electronics in April 1965, and there are reprinted versions in Proceeding of IEEE in January 1998, and in IEEE Solid State Circuit Society newsletter in year 2006. The interest in Moore's law has increased abruptly in the 90s. This plot was done on February 24, year 2023. And here we have the document citation. We have in blue the Scholar Google citation when you look for Moore's law. And in red, you have Scopus when you look for Moore's law. And you see that in the 70s and 80s, there are a few citations. But then in the 90s, the citation start to increase abruptly. And then year 2020 is kind of getting flat. Here is what Morse said about his law in 1975. The exponential increase in device per chip is maintained by 3 distinct factors: increase in silicon die size, reduction in future size, and device and circuit cleverness. And he presented here the number of components per chip and the year, and he see also the exponential behavior. And here is the reference. That was presented in IDN in 1975. Here is Moore's law in year 2003. This was presented in IEEE International Solid State Circuit Conference in year 2003 by Morse. And Morse presented here the transistor density, and here the year, and here there are the different circuits, and he sees that the exponential behavior is maintained. He says something very interesting. No exponential is forever, but forever can be delayed. Here is Moore's law in year 2003. Here is the minimum feature size in the vertical axis, and here is the year, and here he compared the different sizes with another things. For example, the 100 micron is a human hair. An amoeba is 15 micron. Red blood cell is 7 micron, so it's around the year 80s. The 8 virus is 0.1 micron, which is year 2005, and it is increasing. Here we have the power as a function of year. So we have here the active power. The active power is the power that you spend when the devices are commuting from off and on. And then you have here in green the leakage current. The leakage current is due to a current in the gate, and it's the leakage current, and this power is increasing. So for example, in the year 80s, the leakage current was completely negligible. But in year 2000, the leakage current is approaching the active power. So the leakage current is not negligible anymore. So therefore, when you analyze a CMOS inverter from today, the CMOS inverter has a power even though it's not commuting because of the leakage power. Here is the power supply voltage, how it's changing. In the 70s, it was 12 volt, then it decreased below 10 volt, and then keep decreasing, and nowadays it's less than 1 volt. And here is the lithography cost. The lithography cost is very interesting because if you plot here years, and here you cost, you in the vertical axis, the lithography tool cost, this is increasing exponentially. Here is Moore's law in year 2005. This plot was done by our group, and here is the transistor per die. Here are the different microprocessors. Here is the horizontal axis, the year, and if you the fitting will give you the number of transistors per die is following the following equation: 2 to the power year 9050 divided by 194. Let me see, because okay, it's fine. Let's keep the presentation. Because I was listening some noise, so I was I worried about receiving a message. Let's go back here. Okay. So here we have Moore's law in year 2016. Moore's law to year 2016 is to elevate the exponential behavior. And here we have Hiroshi Iwai. Hiroshi Iwai, who is the EDS eminent lecturer, he's the only one EDS eminent lecturer, has recently presented various invited articles and talk about this topic. So here are the reference, and it's very interesting to mention that the last article, it is available in YouTube, and you can watch it in YouTube. According to Hiroshi Iwai, in year 2021, if we plot from the Stone Age, the device dimension were in the size of a centimeter, and this device size was maintained to a 20th century. In the 20th century, the device size starts to decrease abruptly. It goes below 1 micron, and it's now reaching a limit, the practical limit. The practical limit is around 10 nanometers, and this practical limit is larger than the tunneling distance, which is another fundamental physical limit, or the atomic distance, which is also another fundamental dimension limit. Here is the reference. According to Hiroshi Iwai, in April year 2022, here is the reference. This presentation was done in Malaysia. It's available in YouTube. Here with a picture of Hiroshi Iwai when he was giving the presentation. He was asking himself, what is the limit of downsizing? He started by saying, well, no picoelectronic will exist because there is no physical structure that will allow that. So the ultimate limit, the distance between atoms, we cannot reach that limit. The fundamental limit, direct tunneling distance, we cannot reach that limit. So the practical limit is going to be around 10 nanometers. And why is the practical limit? Well, because maybe there will be demerit by downsizing. Demerit by downsizing means if you decrease below that, the prices, the cost will increase so high that it is not a good idea because you cannot sell it. So therefore, you cannot decrease any more than 10 micron because it will be too expensive. According to Hiroshi Iwai, in April year 2022, the practical limit is due to heat generation, leakage current, and metal line resistance increase and reliability degradation. The following item seems to be not very important: lithography resolution, cost increase, production yield, and gate oxide reliability. Here is the reference. According to Iwai, downsizing will reach the limit in 10 years because of leakage current and metal line resistance increase and reliability degradation. 3D integration will keep more slow in the near future. However, 3D integration will reach the limit because of cost and heat generation. Here we have a presentation by Giorgio Baccarani. Giorgio Baccarani is an expert in MOSFET, and here is the reference. So Giorgio Baccarani reviewed the transistor discovery and the microelectronics evolution that was done recently in February of this year. And here is an interesting view graph, the minimum feature size versus technology node. So here we have the minimum feature size, and here we have the different technology node. For example, the 130 technology node has a minimum feature size of 130. And this was the same at the beginning.
It seems Adelmo had a technical issue. With his connection, maybe let's wait to see if he can establish the connection.
So, but it is very important to mention that there is no information from Intel about processor. So if you try to study Moore's law with a recent microprocessor, there is no way that you can do it. Mark Wolf, the director of processor architecture and integration in Intel, he wrote in year 2018, despite occasional report of its demise, Moore's law is alive and well. We have continually invented new material and new devices structure to deliver the expected benefit of scaling, and will continue to do so for the foreseeable future. Here is a reference. And Suman data from University of Notre Dame clarify the confusing meaning of the technology node. The technology node used to be the gate length. Later, it represented half the minimum center-to-center distance, also known as pitch, between the metal line in the first interconnect layer. Nowadays, the technology node has become merely an identifier more associated with the critical transistor density and transistor performance than anything else. Moore's law in year 2020. We have here in blue the number of transistors is following Moore's law, and here we have the performance in yellow. But we start to see that the performance starts to bend down. So the performance is not following Moore's law. Here we have an interesting view graph by Yek Su, who is the director of High Silicon Research, and that was presented in the conference EDTM year 2021. He presented the wave of computer revolution. So he started here with mainframe computing. That was in the year 60s, start to increase, go to a maximum, and then start to decrease. And then the second wave, personal computing, start to increase in the year 80s, go to a maximum in year 2005, more or less, and then it goes down. And then mobile computing start to increase, go to a maximum, and then get flat. And then the last wave is going to be ubiquitous computing. It started to increase now, and it's increasing. And this is ubiquitous computing is due to mobile computing, automotive, and, for example, Internet of Things. So according to Yek-Su, semiconductor industry is poised to grow strongly for the next 2 decades. Here is a reference. And Yek-Su also said the following. Here we have the traditional trend of Moore's law. So here we have, for example, the dollar per transistor. The dollar per transistor is decreasing as a function of year. On the other hand, transistor per chip, which is yellow, is increasing as a function of year. So this is the traditional trend of Moore's law. But he said the following. Per gate cost reverse the trend starting from 5 nanometer node. Therefore, the scaling benefits are diminishing. So for example, 16 nanometer is here. So we have a cost. 10 nanometer, we have a cost here. And from 60 to 10 to 7 is decreasing. But from 7 to 5 nanometer is now increasing. And 3 nanometer is going to increase anymore. So that means the cost per gate is increasing in the very small node. So after Moore's law powered the semiconductor industry for the past 55 years, the industry is poised to grow strongly for the next 2 decades, driven by ubiquitous computing. Here we have a view graph from Haiyun Zhao. He is the CEO of SMIC. SMIC is one of the most important electronic company in China. And he said the following, that was in the conference EDTM year 2021. Here is the reference. So according to him, he presented this view graph, and this view graph describes the evolution, for example, when you start to use high-K metal, when you use the FinFET, and according to him, for example, the 3 nanometer is under research. Well, we have to update this view graph. Samsung began using 3 nanometer in production in June of year 2022, and TSMC initiated production on 3 nanometer in January of this year. According to Chemin Hu, IC industry is going to survive another 100 years. Here we have an interesting circuit which is called wafer scale engine. Here is the picture, and here this is the area compared to the area of a largest microprocessor. And this wafer scale engine has 8.5 10 to the 5 cores. It has an area of 25 centimeter by 25 centimeter. It is fabricated by TSMC using 7 nanometer process. It has 40 gigabytes of RAM and 16 times 10 to the 16 bit per second of memory bandwidth. Here are the reference. Here we have Moore's law in year 2021. Moore's law, according to this, transistor count is increasing, and the chip size is increasing here, and the transistor density, look now, density is still increasing, but now they are not plotting anymore the transistor count. They are plotting here the transistor density. Here is Dennard scaling rule that was presented in 1974. According to Dennard rule, the idea was the dimension was scaled by a factor of 1 over K, doping was scaled by a factor of K, voltage was scaled by a factor of 1 over K, current scaled by a factor of 1 over K, and so on. Here is the traditional MOSFET. Here are the references. Year 1990-20 to year 2000, miniaturization deviate from Dennard scaling rule. So for here, for example, we have the switching energy. The switching energy is decreasing with years, but then around year 2000, it start to deviate from this straight line and start to go like this. And here we have the voltage that the circuit are using. So for example, a 45 nanometer technology is using around 1.1 volt, while a 40 nanometer technology is using less than 1 volt. Here we have the recent innovation used to continue scaling. We have 6th generation of Intel transistor. We have here, for example, a strained silicon. It was used in year 2003. Then year 2065, 65 nanometer. Then in the 45 nanometer, the high-K metal start to be used. And in the 22 nanometer, the FinFET was used. A strained silicon transistor is used commercially in year 2022. The history of a strained silicon is the following. In 1951, Bell Laboratories discovered that the stress influenced the mobility in diodes. In 1992, Welser from Stanford fabricated MOSFET with a stress silicon, which presents 70% higher mobility. In year 2002, Intel used a strained silicon transistor in the 19 nanometer technology. There is a book and a review article dedicated to a strained silicon MOSFET. Year 2007, high-K metal gate transistor. The first MOSFET in the 60s were fabricated using metal gate. In 1968, Bell Laboratories proposed to use polysilicon gate in order to obtain a cell line process. This became the standard process up to year 2007. In 1998, simulation of high-K metal gate transistors were presented in order to eliminate the polygate depletion effect and to reduce tunneling leakage current between the gate and substrate. This work was done by Hewlett-Packard Laboratories in collaboration with universities in California. In year 2005, Mishra et al. Predicted that high-K dielectric material would be part of a mainstream technology. They recently reviewed the high-K dielectric development. In year 2007, Intel used high-K metal gate transistor in a 45 nanometer technology. Here is the abstract when they presented this news. This news was presented in the IEEE spectrum. Why do we need new transistor structure? This is a good question. I recommend you to see this presentation by Su Jae-Kin Liu, FinFET History, Fundamental and Future. That was in the Symposium of VLSI Technology short course in year 2012, but here is the link and you can download the presentation. So leakage current occurs in the silicon away from the channel. The body of the SOI silicon on insulator SOI MOSFET is very thin. Therefore, the leakage is smaller in SOI devices. Here we have the regular device. So this is very thick. On the other hand, here we have an SOI MOSFET. Here we have an oxide. The silicon is just here. So this is very thin. So because of that, the leakage is smaller. Here we have an SOI. We will talk about SOI silicon on insulator. It is interesting to mention that the original motivation for SOI in the 80s were the following: suppression of flash up, greater immunity to radiation, and the possibility of three-dimensional integration. Here are some references. Research on SOI MOSFET started in the 80s with the fabrication of laser recrystallized polysilicon SOI MOSFET at Texas Instruments. The double-gate SOI MOSFET was proposed in 1984, and it was fabricated in 1989 by Hitachi. This device contains the essence of the FinFET. Single crystal fully depleted SOI MOSFET were fabricated in 1987 using CMOS at Hewlett-Packard. Here are the references. In 1998, the first FinFET was fabricated by Hitachi in collaboration with University of California, Berkeley. In 1999, the IBM selected SOI for next generation microprocessor. It is interesting that Texas Instruments initiated the research in SOI, but it was IBM who took the SOI to the commercial level. In year 2003, Infineon developed nanoscale FinFET for low power application. In year 2005, IBM, Sony, Toshiba developed a 64-cell processor in 90 nanometer SOI technology. In year 2012, Intel used fully depleted FinFET in the 22 nanometer technology with high-K metal gate and channel strain technique. Here we have the multi-gate three-dimensional SOI devices. This is a single-gate SOI MOSFET. In green is the gate, in white is the oxide, and in blue is the silicon. We have here source, we have here drain. The device is on top of an oxide. That's the reason it's called silicon on insulator. And the gate is here, and it's only a single gate. Here we have a planar double gate SOI MOSFET. So we have a gate here and a gate here. We have the silicon here. This is source, this is drain, and this is oxide, and this is oxide. A gate on top and a gate on bottom. Here we have the vertical double gate SOI MOSFET. So we have here source, we have here drain, we have here oxide, we have here oxide, we have here a gate here in this side and a gate in the other side. So we have here the triple gate SOI MOSFET. The gates, all of these. This is oxide, this is source, this is drain, and all of this is on top of an oxide. Here we have the gate all around SOI MOSFET. So the gate is going all around. Here is source, here is drain, and this is oxide. And this is on top of an oxide. The gate all around MOSFET inspired the nanowire device. Here is the gate all around MOSFET. Here is source, here is drain, this is oxide. And the idea is if you take this structure and you copy this structure here, and then you put another structure like that one on top of it, and another one, so this is called the nanowire. So the nanowire is like the gate all around, one on top of the other. Here is the reference. The double gate MOSFET structure could be planar, for example. Planar because this is drain, this is source, and the current is going like this. The top gate is here, and there is a bottom gate here. So this is double gate, but it's a planar structure. Could be vertical. Vertical means drain here, source here, the current is going like this. We have here a gate, and we have here another gate. Or could be type of FIM. FIM means source here, drain here, current is going like this. There is a gate here, and there is a bottom gate in the other side. Here is the reference. My mouse is missing. Let me see. Okay, I found my mouse. Okay. The Delta SOI MOSFET. The Delta SOI MOSFET was proposed by Hisamoto from Hitachi in 1989. It is a double gate MOSFET, and it contains MOSFET. 1998, the first FinFET was fabricated by Hitachi in collaboration with UC Berkeley. Here is a reference. Year 2012, Intel used fully depleted FinFET, and that was in the 22 nanometer technology with high-K metal gate. Here we see a transmission electron microscope of a FinFET. Here is an interesting view graph. The interesting view graph is the following. In year 2002, the number of players with a leading-edge logic fabrication technology were 25. In year 2004, there were only 18 players. In year 2006, there were only 13 players. And if we go to year 2014, there were only 4 players. The 4 players were Global Foundry, Samsung, TSMC, Semiconductor Company, and Intel. The previous spot, in year 2016, we have 4 players: Intel, Global Foundry, TSMC, and Samsung. In year 2019, there were only 2 players working with the 5 nanometer node, TSMC and Samsung. In June 2022, Samsung began chip production using 3 nanometer process technology with gate-all-around architecture. TSMC started 3 nanometer chip production in January of this year. Here we have a view graph from the International Roadmap for Devices and Systems. In this device, we have in the vertical axis the dimension scaling, and in the horizontal axis, we have the year. So we have the dimension scaling, how it's being reduced, and it's very interesting to know that the smallest dimension is always greater than 10 nanometers. So 10 nanometers is the practical limit. Here we have another view graph from the International Roadmap for Devices. So we have in the first one on top, the number of gates, the number of gates per area, and we see that this is increasing. We see that the megabit per area, the density of megabit per area is increasing. We have the number of core in the microprocessor is increasing. Here we have a view graph from the International Roadmap for Devices, and here is presenting the scaling scenario. The scaling scenario is the following. We started with planar devices. Among the planar devices, we have the bull device, the classical bull device, the partially depleted SOI devices, which is still planar, or the fully depleted SOI device, which is still planar. But then we have non-planar devices, like the FinFET, like the bull FinFET, like the SOI FinFET, and the gate-all-around. The gate-all-around could be done vertically, or could be done also lateral, and could be done in lateral in 2 ways. It could be SOI, or could be a device with a connection to the body. It is very interesting. FinFET is the nano chip, and the nano chip inspired the nanowire, and the nanowire inspired the nano chip. The difference between the nano chip and the nanowire is that the lateral dimension is larger than the vertical dimension in the nano chip device. Now let's talk about the recent development and critical challenges. In June 2022, Samsung began chip production using 3 nanometer process technology with a gate-all-around architecture. Taiwan Semiconductor Manufacturing started chip this year. In 2019, TSMC and Samsung presented 5 nanometer manufacturing process. The 5 nanometer node was the first to be built completely using extreme ultraviolet lithography. There are only 2 companies using 3 nanometer technology. Global Foundry stopped at 14 nanometer. Intel is using 7 nanometer technology so far. Global Foundry, CA, Leti, and SOI Tech and ST Microelectronics announced a new collaboration in fully repeated SOI technology on April of last year. Fully repeated SOI is used for automotive, Internet of Things, and mobile applications. Global Foundry and ST Microelectronics announced in July of last year that they are building a jointly operating manufacturing facility in France. This new facility will support several technologies, in particular fully repeated SOI-based technology. In year 2019, Malinowski from Global Foundry predicted that FinFET technology will be dominant until year 2021. He was right. This decade of FinFET will be finished because of technology challenges. He is right. In addition to the enormous cost of manufacturing and technology development, the IC design costs are also increasing with the new nodes. For example, the 28 nanometer, it costs $50 million. 7 nanometer, it costs $300 million. And the 5 nanometer node costs $500 million. After year 2025, classical CMOS technology and Moore's law will end. Well, we will see it. Graphene or carbon nanotube are not planning in CMOS mainstream manufacturing in the near future. I agree with him. The gate-all-around of FinFET, what is the device that's going to be the device of the future or the present? Well, Samsung presented a 3 nanometer gate-all-around in year 2021 and began chip production in June of last year. Taiwan Semiconductor Manufacturing plans to stay with FinFET for the 3 nanometer node. Intel is researching in the gate-all-around transistor, and they are using the name of ribbon FET. IBM is also working with the gate-all-around transistor. Samsung began chip production using 3 nanometer process technology with gate-all-around architecture in June of last year. This is a picture when they announced it. Samsung announced in year 2019 that the gate-all-around will be used for the 3 nanometer node. And here they presented the evolution from planar FET to FinFET, and then the gate-all-around, and then the nanosheet. Taiwan Semiconductor Manufacturing Company is using the 5 nanometer process technology, which entered in production in year 2020. The 3 nanometer technology entered in production of December last year. Taiwan Semiconductor Manufacturing Company, Arizona First Fabrication Lab, is scheduled to begin production of 5 nanometer process technology in year 2024. The Taiwan Semiconductor Manufacturing Company has also started the construction of a second fabrication, which is scheduled to begin production of 3 nanometer process technology by the year 2026. The investment will be US $40 billion, representing the largest foreign direct investment in Arizona history. Here we have an interesting idea presented by Intel in year 2020 in IDM. The idea is, on the left side, you have a planar device. This is a conventional device. Then you go to the FinFET. The FinFET, it was a good advance. Then you go to the nano ribbon, and the nano ribbon, you have a P channel and an N channel, one next to the other. The idea is to go one step forward. Now, instead of having one device next to the other, we have one device, one on top of the other. So we have the N channel on top of the P channel. In that way, we are saving area. This is a view graph presented by Synopsys in IDM year 2020. He said scaling began slowing after the 10 nanometer node and is expected to practically finish by the 1 nanometer node. Transistor density is expected to continue increases at 20% per year due to design technology co-optimization and electronic design automation. And here on the left side, we have a view graph where he presents, for example, the technology node in the horizontal axis, the contribution in the vertical axis. So for example, for the 100 nanometer node, the contribution of scaling was 80%, while the contribution of the software, EDA and DTCO, is about 20%. On the other hand, if we go to the right, to the figure, the projection for the 1 nanometer node, on the figure in the right side, for the 1 nanometer node, the contribution of scaling is going to be less than 10% for the 1 nanometer node, and the contribution to DTCO and EDA will be larger than 90%. Now we have a view graph presented by TSMC and IDM last December in IDM. They reported MFET with EOT of 1 nanometer and narrowly ideal threshold swing of 68 milliwatt per decade. It is interesting that they extract the threshold voltage using the constant current method. And here we have a summary of what Ann Keller is the Intel Executive Vice President, and she presented this in IDM last December, and she said the following: Moore's law predicting functional integration increase over time continue to be built upon a foundation of semiconductor process scaling. Moving the power line to the backside of the wafer, a technique called power via, enable more cell height and performance scaling than the simple geometric screen. The next major architecture for transistor scaling, called ribbon FET, or all gate-all-around. Advanced package will play an increasing larger role in enable power, performance, area, cost, time to market, design flexibility, and reliability. Power, thermal, and routing constraints are bottleneck to three-dimensional IC scaling. The industry may revisit 3-5 compound semiconductor for NMOS and germanium than silicon, and thus be capable of more efficient circuit performance. Now let's talk about RF application. The wireless market was traditionally dominated by bipolar junction transistor and MOSFET. Because of the downscaling of CMOS, the MOSFET is now used for low gigahertz range application. University of California, Los Angeles presented the first full CMOS RF amplifier in year 1993. This is very interesting because I went to graduate school before that, and I used to remember that, the RF application was not for CMOS, and nowadays CMOS is getting to be dominant in the RF application. Samsung used 14 nanometer FinFET in RF application. TSMC used 5 nanometer FinFET in RF application, and the references are there. Here we have some view graph presented by Raskin, and that Raskin presented this view graph in LAADC in April year 2021. According to him, depleted the SOI MOSFET with channel length of 90 nanometer to 160 nanometer is the mainstream technology for RF SOI system, and fully depleted SOI MOSFET is the most promising candidate for future wireless communication. Conclusion: we have reviewed the evolution of semiconductor device. Moore's law is approaching the end, and it is partially surviving because of device and circuit cleverness. FinFET are the dominant devices in CMOS technology for high-speed use in microprocessor and wireless application. The FinFET are being replaced by the nano chip, which is also called gate-all-around, nano-beam, nano-ribbon, ribbon FET, or multi-bridge channel FET. Fin da apresentação. É uma honra, é um prazer visitar o Brasil. Eu realmente agradeço este convite. Será un placer enviarle una copia da minha apresentação se você solicita por e-mail. Mi email is ortiz@ieee.org. Gracias. Thank you. Obrigado.
Gracias. Obrigado, Adelmo, for your great presentation. Thank you really very much. And the audience that is watching over YouTube, you can type your questions on the YouTube chat, and we are going to read it to Adelmo. There's still a question that is from Diógenes Marcano from Simão Bolívar University. And Diógenes Marcano asked Adelmo, thank you for this conference. According to your experience, what is the limit in semiconductor technology? Can artificial intelligence be applied to these technologies?
Let me get rid of first. I am fighting with the computer.
Okay, please take your time, Adelmo. Take your time, please.
Yes. Okay. So I should stop screen, no?
Yes, already stop. You already stopped sharing the screen, but don't leave the studio. If you leave the studio, we'll be
okay. No problem.
be
Okay.
disconnected. Okay, but
okay, perfect.
Yes,
so the question, if I understood, is are we is the artificial intelligence going to be applied to a semiconductor development? That is
yes.
the question, isn't it? Well,
yes,
definitely it will be. This is why Synopsys is saying, and maybe let me go back to. I still can I show the presentation, and let's see.
Yes.
Okay, present. Let's go back to share screen.
Okay.
Share screen. Okay. Entire screen. Okay. Are you watching my screen now, no?
Not yet, but I think it's not yet, Adelmo. Yes, now yes. Yes, now we see your screen.
Okay. Okay. Right. Okay, there is a view graph that is a good answer to that question. Let me show it to you. That's the reason I wanted. Synopsys. This view graph, for example, let's look at the right side of the view graph. Let me see. If you see this here, we have here the technology node, and here we have the contribution. So if we look at 100 node, that means an old node, the contribution of pitch scaling, that means downsizing, is 80%. And this is a contribution of the software in which artificial intelligence will play an important role. The software is what they call design technology co-optimization and electronic design automation. That has to be this has to do with software and in artificial intelligence, of course. So by this node, the contribution is only 20%. But what they are projecting or what they are expecting is for the 1 nanometer node, scaling will contribute to less than 10%, while the software and the artificial intelligence will contribute to 90%. So definitely the answer is yes. It will be very important.
Yeah, software and tools like artificial intelligence are becoming even more important. Is that what you mean, right?
Yes.
Yes, okay. Thank you, Adelmo. There is another question. The next question is from Juan Pablo Martinez Brito. Can you clarify more on the distance of 3, 2, and 1 nanometer in current technologies? This distance refers to what currently? I know that's no longer referred to the channel length. I mean, the feature size is probably he's asking what the feature size mean today. You know, you have that slides where you show the technology node and the feature size. I will read the question. Okay.
Let's go back to that one.
Yeah. So we want you to comment more and qualify that. What does the distance or the names 3, 2, 1 nanometer actually mean? Since it does not mean the channel length anymore.
Okay, here is what Suman Data said. And the problem was, if we go, for example, to the 90s or to the 80s, when you said in the 80s, the technology was 10 micron, that means 10 micron was the channel length. And that was very simple. If you know it's a 10 micron technology, it was 10 micro channel length. The problem was in the recent development, the downsizing is not anymore with the channel length. The downsizing has to do with something around the channel length. What I mean is the device has a channel, of course, and the device has some other part. You expand some area, for example, to contact source, to contact drain. So the idea is they are increasing the density of the devices, not because they are reducing the channel length. The channel length is not being reduced anymore. It cannot be reduced anymore. It reached a limit, I think. The problem is what they are doing is they are reducing the sizes, for example, of the contact of source and drain, and all the sizes between one metal line and another metal line. And by doing that, they are increasing the density. So then what they do is in the latest technology node, the technology node doesn't mean the channel length anymore. No, not at all. The technology node has to do with the density. So when they tell you the technology node is 3 nanometer, for sure the device has a channel length larger than 10 nanometer, for sure. And the idea is they have reduced so much the other areas that it is like having an effective channel length of 3 nanometer. But it's not that the channel length is 3 nanometer. No, no way. Definitely no. I don't know if I answered the question. Maybe let's see if here is a plot of Pacarani also. This plot, it was presented by Pacarani, but actually it was presented originally here by Sikar and Truman introduction. And the idea is in 3 nanometer node, the dimension is a lot larger than 10 nanometer. And it will be like that in the near future. I don't know if I answered the question or I am missing something.
I think so. I think you answered the question. And Juan said, I'm a huge fan. Juan Pablo Martinez Brito, the one that asked the question, said, I'm a huge fan of your work, Professor Adelmo.
Thank you. It's good to know that your word is being used somewhere, because sometimes you get frustrated. So very nice. Thank you very much. Obrigado.
And there is one question by Enrique Kessler. Once the 3D scaling is explored, is the single core performance doomed until a new material is found? What are your beliefs? I will read again. Once the 3D scaling is explored, is the single core performance doomed until a new material is found? What are your beliefs?
Well, I think the 3D integration is very interesting because that was the original motivation in the 80s when I was starting my graduate work at the University of Florida. That was a dream, SOI to be used for three-dimensional integration. Nowadays, it's not a dream anymore. It's a real situation. The 3D integration is being used, and the problem with the 3D integration is that you will be able to keep increasing the density of devices, but the problem will be the heat. The heat will limit the integration. And with respect to using one core, well, I am not an expert in digital, but my guess is the following. Nowadays, they are using the idea of using a single core is over. They are using multiple core, and the idea of using multiple core, well, now if they use three-dimensional SOI integration, it's just a matter of technology. Probably they will be using in the near future, or probably they are already using. I don't know the answer. I don't know if I answered the question or I am missing something.
Yes, I think so. Yes, I think so, Adelmo. Thank you very much. There are no more questions there, and also we have over the time because usually the talk with question and answer expected to be 1 hour. We are a little bit over already. So thank you very much, Adelmo, and I also would like to Yes, both Pablo and Enrique, they confirmed the ones that asked the question that you answered the question. They thank you for the answer, Adelmo. I'm reading the YouTube chat. And I also would like to thank very much Professor Sandro Binso Ferreira from Unicinos. That's our chapter vice-chair or co-chair that's managing the streaming in the backstage. So Sandro, thank you also very much for your help here. Without you, this would not happen. And thank you again, Adelmo, for your great work, and for sharing it with you. I also, like Juan, I like your work very much. I read a lot of your papers, and yes, I like very much your work. I learn a very lot from your work. So thank you. Thank you very much, Adelmo. It's always a pleasure
Obrigado, muito
to have a
obrigado.
talk with you. Yes, and muito obrigado, because now we're over the 1 hour time slot that we have for the and as Adelmo said, you can always send him an email and ask him question and get in touch, right, Adelmo? If you could briefly show again for the closure your email, I think is at the first or the last slide, so that we can close the section if there's no further questions.
Okay.
Okay.
Here is a.
Yeah, here's the email. Here's the email. You also, yes. So thank you very much. Thank you, Adelmo, and thank you everybody for the audience. It was a great pleasure this webinar today. And Sandro, so if you can stop the streaming, Sandro, we will thank you very much. Thank you. Thank you so much.